Okay, class, let's go through some solutions to the exam. This will give you a chance to self-grade yourself before I get a chance to grade them, and I will start working on that as soon as I can. But you're probably curious on how you did and what the correct answers are. I think you can look on Canvas, and they get unmuted at midnight tonight. But everybody's done with the exam, so I thought, okay, why don't we go ahead here and give you the solutions here. So starting with question number 1, it says, your instructor rides on a merry-go-round. So the big thing is we're going in a circle. This is right out of chapter 6. At a constant rate. In which direction does the net force on you point? And so remember, F equals ma, and the point of this was to say that there'd be an acceleration towards the center of the circle, and so I guess that would make this option, towards the center of the circle. It would also be equal to v squared over r. I don't know if that's listed or needed, but towards the center of the circle is the correct answer. Okay, so number 2 says Mercury has a radius that's about 38% of the Earth's radius, and it has a mass of, it looks like, about 5.5%. Estimate the acceleration due to gravity. Now, this actually is also chapter 6, where you might think about it as, capital M, little m is how we wrote it, as the force of gravity, and also remembering that acceleration is force divided by mass. So we saw here in class that the acceleration on the surface of some kind of planet would be a combination of factors of the mass of the planet, the radius of the planet, and then this G I'll just call nature, the universal factor. It's the same for every planet, so it's not unique for that planet, but the mass and radius is, so therefore the acceleration due to gravity would be unique. Now, one option, I'll call it the long option, is to go ahead and look up the mass of Mercury and the radius of Mercury, but then you wouldn't need their information. But it's a lot easier if you use their information, because I'll just do it like this. G, the mass of Mercury, they say, is 0.055 of the mass of the Earth, and I'll put a little E down there. So mass of Mercury becomes 5.5% of the mass of the Earth. And the radius is 0.38 times the radius of the Earth. So the radius of Mercury. See, the reason that's useful is if you take the numbers and kind of group them together, then you'll have the G, the mass of the Earth, the radius of the Earth squared. And if you give that some thought, that would be the acceleration on Earth, which is 9.8. So all we need to do is take the 9.8 and multiply it by these prefactors. All right. So I'll do the prefactors, 0.055 divided by 0.38 squared. So that's the prefactor times the 9.8 is about a 3.73. So must be B also. Okay. Moving on to question 3. It says a boxcar traveling at 10 meters per second approaches a string of 3 identical ones. 1, 2, 3, and we've got 1 that's moving. These are sitting stationary on the track. The moving car collides and links, so they stick together, with the stationary ones, and the 4 move off together along the track. What is the final speed of the 4 cars immediately after the collision? So, again, that principle of conservation of momentum comes into play here. I guess this is chapter 8 on momentum. But what we would say is look at the total momentum of both objects. That's probably the big thing to remember. Momentum is only conserved if you look at both items, or all 3 if there's more interacting. But thinking of these 3 as 1. But either way, I can think of them in all 4, or think of it as 2. but I'm going to use all of them. And so I would say it's the mass of the first one times the velocity of the first one, and the other ones aren't moving. So they're zero. Okay. You could even put in the mass of the boxcar. They have it, but that's just kind of a waste of time, because on this side, you can think of the four hooked together as 4 times m of one of them. Because they do say moving by cars stationary, the 4 move off together. What is the final speed of the 4 off together? You may assume that the mass of each boxcar is this 18,537. And so you could put that in or not, because calculating the momentum after is 4 times that mass, and the mass would cancel off. So we really don't need the 18,000. All we really need is to realize that the final speed is 1/4 of the initial speed, because basically we've taken this moving object and made it 4 times more massive. Therefore, the speed has to go down by a factor of 4 in order to have the same momentum. So 10 divided by 4 is 2.5. And so it looks like D would be the right answer there. Now, number 4 is a hard one, or at least would have been a hard one if it wasn't for exactly I did this problem in Chapter 9 supplemental lecture, except I think the one I had a physics textbook instead of a bowling ball, and the dimensions were a little different. And it looks like mine didn't print very dark here, so I'm going to do a pivot point. But the biceps is pulling up, and so I'll say force of bicept. And it looks like they're trying to say it's 4 centimeters away. And so the biceps here is making everything rotate from the elbow, and so the bowling ball and the arm would rotate up. That's a counterclockwise, so I will call that a positive torque. Whereas the other 2 torques, which would be the weights of the bowling ball making the arm go in this direction, so that's a clockwise direction around the elbow, so that's a negative torque. But also the weight of the forearm is going to make it go in that direction. So we have 1 positive torque and 2 negative, but the idea was to hold it there. The second condition of equilibrium is that the sum of all the torques is 0. So knowing that, I'll do the positive one. This would be the 4 centimeters times the force of the bicep. And then minus, and I'll do the forearm here. I think in here they say bowler holds a 7.2 kilogram bowling ball in the palm of his hands as shown. The upper arm is vertical, and the lower arm, which has a mass, there it is, 1.8 kilograms. So to get the total weight of the arm, I'll take the 1.8 kilograms and multiply by 9.8. And the distance out looks like 15 centimeters. So there's the negative torque from the weight of the forearm. Important, not nearly as big as the second part of this, the negative torque from the bowling ball. So I'll put a negative. And the mass of this bowling ball is 7.2 times 9.8. And its distance out is much further. Of course, it's in your hand, so it's 33 centimeters. So, of course, this second condition of equilibrium allows us to solve for the only unknown, the force from the bicep muscle. So let's figure out these negative torques. 1.8 times 9.8 times 0.15. And another negative torque is the 7.2 times 9.8 times 0.33. So those are the 2 negative ones, and I'll kind of in my mind put them together. I know my calculator, I just didn't even do the negative. I just did the positive. But I only did that because I knew then once I get these 2 negative ones, I'm going to move it to the other side of the equation. So now it's positive. And then I can divide it by the 0.04. and get a force of about 648. So it looks like C would be the correct answer for number 4. Okay, moving on to number 5, says a material scientist makes a new light strong material. Okay, sounds good. The scientist places this new material in water, and it floats with 25% of the object above the water. What is the density of this new material? Well, since 25% is above the water, that would mean 75% is under the water, and part of our Archimedes principle said that the percentage underwater is the same as the ratio of the densities, and since water has a density of 1, this is going to be 0.75. But maybe I should work that out. When something floats, and so I'll take a little object and make the water level, we're saying that the buoyant force is equal to the weight of the object. So you would have mass of object times g, and the buoyant force would be weight of the fluid displaced times g, and I guess we can cancel off a g. Now, the mass of the fluid displaced would be the density of the fluid times the volume of the fluid displaced, whereas the mass of the object would be the density of the object times the volume of the object. And when you float, in the picture right here, the volume of the fluid displaced is something less than the volume of the object. So I will put those together and then point out it'll be the same ratio as the density of the fluid compared to the object. So they're giving this number indirectly. Like I said, this number is 0.75 because this is the amount underwater. And so this says this is above the water. So I guess there's a little subtlety there that hopefully you won't overlook. Because if you overlook that, you might pick this one by mistake, the 0.25. Okay. But this right here is the amount under the water. And then, of course, the water has a fluid of 1 gram per cubic centimeter. You can look that up, or hopefully you've memorized that one from our fluids. That's kind of the, standard definition here of a gram. But either way, we would get 0.75 grams per cubic centimeter. So didn't expect you to work this equation out, just kind of expect you to know it, or to open up your notes and get it from your notes. I did a floating object in class, and I also know that the book has it there. Okay. On to question number 6. 6 says, if you have 2 cubes of the same size, one is made out of wood and the other is made out of aluminum. Both cubes are placed in a water-filled aquarium, and the wooden block floats and the aluminum block sinks. All right, so maybe I'll draw a picture, and here will be the water level. The wooden one floats, and of course, what we just talked about, part of it would be kind of out of the water, depending on the ratio of the density of the material compared to the fluid. Most of your woods are around 1/2, so about half it will be underwater and half will be above. But there are some higher density woods where it would be less than 1/2. And I even showed you a high density mahogany that sank because it had a density greater than 1. But this one's got to be less than 1. It does float. But here's the question. Which one, if either, experiences a greater buoyant force? And even though it doesn't float, it's actually the aluminum one. And that always, I think, catches people off guard. They think, well, it's obviously, they go, the other one floats, so it must be pushing up more. But no, remember the buoyant force is equal to the weight of the displaced fluid. So if anything's floating, it's going to be displacing less than a fully submerged one. And a fully submerged one then has a larger buoyant force. I mean, it only does it. The only reason it doesn't float, even though the buoyant force is greater, is that its weight is also even much greater, and so it ends up sinking because its weight is more than the buoyant force. But comparing these buoyant forces, this one's actually bigger, yet this one does float because the buoyant force, if you pushed it all the way down, the buoyant force would be more than its weight, which would push it back to the top. All right, so there's a nice little conceptual, if you will, Archimedes one. All right, so question 7, if it takes 2.52 joules of energy to compress a spring 7 centimeters, what is the value of the spring constant? So this was a kind of a plug and chug into the equation for the potential energy. It does have a little bit of unit conversion that you got to be careful with, because energy is measured in joules, which has buried inside of it a meter. So don't overlook the unit conversion from back to chapter 1. Easy to do. But here's joules and here's meters. I can now solve this for the K value. So 2.52 and then multiplied by 2, then divided by 0.07 squared. And it looks like we're at 1,028, or the three significant figures, 1,030. So that would be the spring constant. And I think if you don't convert your units, you're going to be changing this by 4 decimal places, right? 1, 2, 3, 4. So you probably would jump on and incorrectly to that one. All right, so number 8 has a hollow ball that rolls down a hill from this height. And again, watch your units. It's in centimeters, so just like number 7, back to chapter 1, watching our units and converting our units. Okay, assuming no energy is lost due to any kind of friction or heat. So in other words, it rolls down the hill. And so starting at a height, and I'm going to put 0.72 meters. What is the translating speed of the hollow ball? Well, again, this is a conservation of energy from chapter 7, so hopefully the first thing you did is say mg, and I'll call it y initial. I suppose I could even call it mgh, kind of like your book does. I'm a bigger fan of the y's because I can put initial and final. I guess I can put initial height. But then where does that energy go? And when the ball gets down here, it's important to remember that it is both translating and rotating. And so that's what this problem is centering around. You could easily forget that the ball is rotating and just set it equal to that. But that wouldn't be right, because you'd get a speed too big. Because you'd be saying all the energy goes to its translational motion. And that was part of my lecture, was to say that, some of the energy has to make it rotate. Therefore, we would have something less translational speed than this one. That's why, if you remember in the video lecture on this, I kept rolling down the disc and the hoop just to show you. And I compared it to a cart, something that didn't rotate. So for the one that didn't rotate, it went the fastest because we didn't have this term. And so the disc and the hoop had this term. And so they went slower than the cart. And the hoop, this one was bigger, so the hoop went even slower than the disc. Okay, now for us then, that would mean something like this. Now, I don't think we are told the mass or the radius, and that might feel a little bothersome at first, but let's just keep going. Let's put in what we do know. We know the height. I guess we also know g is 9.8, but keeping that in mind, I don't know the mass. There's a 1/2 m and translational speed squared. But this is going to be kind of the magical step. If we go back and we look up a hollow ball, we'll see that the moment of inertia in the little chart is 2/3 of the mass of the ball times the radius of the ball squared. And that works out perfect because the angular speed is equal to the translational speed over the radius of the ball. And now my concern about not knowing the radius of the ball goes away. They end up canceling off. So in other words, this wouldn't matter how big the ball is in terms of the size. So a big ball or a small ball, as long as it's hollow, is going to have the same speed down the hill. And likewise, the mass doesn't matter. And so regardless of the mass, they have the same speed. We can also cancel a 2 there. So on this side, we have the 9.8 and we have the 0.72. And here we have a 1/2 plus. It looks like we have left 1/3 v squared. So I can think of a 1/2 as 3/6. Because I can think of a 1/3 of 2/6. That's a common denominator. So this would be 5/6 v squared. So if I bring the 6 and the 5 to the other side, multiply by the 9.8, multiply by the 0.72, I'm going to get velocity squared. So grabbing my calculator here, I've got 6/5, and I'm going to multiply that by 9.8, and I'm going to multiply that by 0.72, and then I'm going to take the square root. And so it looks like I'm looking at about a 2.91. And so it looks like A for number 8. And that's a hard one. Maybe that's harder than the bowling ball one. But either this or the bowling ball one, I think might be the hardest of the multiple choice ones. Looks like I got another conservation of energy here. This one says we've got a 4 kilogram block sliding across a horizontal floor with an initial speed of. So you might say that is telling me both its momentum and its energy. If the coefficient of friction is 0.35, how far will it go? Okay, so they're talking about distance. They're giving me friction. I think this is appropriate for energy. So I'd say initial energy is equal to final energy. And so the initial energy is just 1/2 mv squared, and it eventually becomes the force of kinetic friction times distance. And the force of kinetic friction, well, this is going to take us back to chapter 5, is the coefficient of friction times the normal, which is mg, and the distance traveled. And so technically we could do this problem without knowing the mass. But they do give us the mass, and so I'll just use it as a 4 and a speed of 8.5 squared. So that calculation is the energy. And then the coefficient is 0.35. The mass is, again, a 4. And g is 9.8. And then we can get distance. In fact, maybe I will cancel the 4. I'm not going to waste my calculator time. So 1/2 times 8.5 squared is this number. Now if I divide that by 0.35 and divide that by 9.8, I'll get a distance of about 10.5 meters. So I guess that's D, and how far does it go? All right, one more on the multiple choice. And this is more conceptual. It's about the rotational inertia. And we talked about it being at an M and where it's located. And if we just had a single object, if you had an object like a disk, you'd have to add up the little chunks of mass. But either case, the whole point of the moment of inertia I was to tell you its resistance to change. And of course, more mass makes it harder to change, but also at a greater distance away. And so that's what it says here. The rotational inertia of an object increases as its mass increases, and its distance from the mass from the center of rotation increases. So I guess A would be the conceptual picture of that. Okay, well, there's the multiple choice. I hope that went fairly well for you. Let's try the free responses here. And so the free response, it looks like we're going to drop a metal object from a height of 48 centimeters on a spring that's vertical. And then it asks how much does it compress? To which maximum distance does it compress? So again, we're talking about energies here. Because we're talking about, motion and distances, and more importantly, how much a spring compresses. So I guess that's distance. But also, velocity is indirectly in here because we start from rest and we finish at rest. So if you say it starts up here, you might say it just has an mgy initial. And where does all that energy go? Well, not worrying about the in-between, eventually it's going to compress this spring and come to a stop. And so you might say then that all of this energy now goes to a compressed spring. You might say final. So notice I did not put an 1/2 m or 1/2 kx squared over here because the initial of the spring was 0. And I also did not put the 1/2 mv squared because its initial kinetic energy is 0. But also on this side of the equation, even though it gained some kinetic energy, it later then lost that kinetic energy. I suppose we could have made this harder on ourselves and done kind of an intermediate. An intermediate, we could say, well, it fell from a height of h, and then when it gets here, it has only kinetic and no potential of compression or what we call an elastic energy yet. Of course, then we would have to continue the problem, but it's, again, all the energies are the same, so, why do an intermediate? Nobody would hopefully calculate the speed halfway down and then calculate it again 3/4 of the way down, and then again right before it makes impact, and then again at the bottom. I mean, all of those you could do, but the energies are all the same. And so let's just get to the grand finale. Let's just go to when it compresses it. Now, there is one thing very, 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 very important here that I've said about potential energy, and that is over here, if I don't have a term, mgy final, I am essentially saying that the final position is 0. And so I like that. I like that because mathematically, this one goes away. I just need to point out that 0 height would be after it compresses. And the reason that's important is because the height they give me is just above the spring. But that's not where I'm calling 0. And so there's an extra distance that the spring compresses. In other words, my initial height is h plus x. Because I'll say it again, in case you missed this, this is going to, I think, be easily overlooked by some of you. It'll be interesting when I do the actual grading here, that it's really easy to overlook this one. But if you're going to call the potential energy on this side 0, that means you are measuring your height from the compressed position, which means then your initial height is this compressed distance plus the height h that it started above the vertical spring. So there really needs to be an h plus x in this term. All right, so that means the math looks like this. mg h plus x is equal to 1/2 kx squared. Well, I'll need some more space to work this out, so let me grab my yellow pad here. But if I put in these numbers, 2.25 is the mass, and g is 9.8. The height is 0.48, and the x is the unknown. Now, the other side of the equation is 1/2 the 1,550 and an x squared. So grabbing my calculator, I'd get 2.25 times 9.8. And so this together is 22.05. And then if I do the distributive property, the first one would be times the 0.48. Let me hold off on that one because I just want to write 22.05x for the second term. The first term then would be to take this number and multiply by 0.48. So that'd be about a 10.6. So there's the two terms I have. Okay. Now over here, I guess half of 15 is 7.5, and half of 50 is 25. So that would be 775x squared. So because of this extra factor of x, the math is a little bit harder. If I didn't have that, it would be a little bit easier math. So again, I have a feeling there's a number of you that have forgotten this extra height, which not only is that a mistake, but maybe the good side of your mistake is you came across some easier math. But this is a quadratic equation. So let's write it in the standard form of 0 equals 775x squared minus 22.05x minus 10.6. So I'll move everything to the right-hand side and then say x equals, and so I'll take the opposite of b plus or minus b squared, 22.05 squared, minus a 4 times an a, 775, times a c, and that is a negative 10.6. And if it'll be okay with you, I'll just merge the negative with the first the negative, so it becomes a positive. And then all over 2a. Which, by the way, now looking at the math here, this number, 22.05 squared, without this would be just 22.05 by the time you squared it and then took the square root. So what I'm saying is all of this is actually bigger than 22.05. So if I use the negative sign, I would get a negative x, and if I use the positive, I get a positive x. Thinking about what I did over here, and you could have done it either way, but the way I treated my x is I treated it as a positive number, right? I said that the height was h plus x. You could have done h minus x and treated x as a negative number. It's kind of your choice. However, what I like to say is you have that freedom of choice, but once chosen, it has power over you. So you need to remember that when you come over to here, and what I like to call read the math, we need a positive value. And so because of that, the one that's going to be a negative, I can not worry about it. It's got another interesting meaning, but in the interest of solving this, let's not worry about what the negative might actually mean if we read the math. But let's just say that we know by reading our equations that we set up. Like I said, you could have set it up either way. It's your choice. But if you pick the way I did it, I picked a positive x, so I got to stick to that. Now, if I had picked a negative here, then I'm picking the negative one, so I'd stick to that. Of course, I'd have a slightly different equation with a negative there, but in fact, what would happen is that would be a negative, which I move over to be a positive, so right here would be a negative, and it goes with the negative, and then, anyways, and I'd choose the negative one. But now I can put in my numbers. So 22.05 squared plus 4 times 775 times 10.6. And then taking the square root of all of that, like I said, is bigger, quite a bit bigger than the 22.05. So taking the plus here and adding the 22.05, that's the numerator. Then I need to divide it by not only a 2, but 775. And so that would be 0.132 meters, or maybe about 13.2 centimeters if you want. But ta-da! There is the first answer to the first free response using the principle of conservation of energy. But also being really careful right there with the height and the meaning of it, so I don't skip anything. Okay, so I'll try 11B, and I'll come back if I need more paper and more room than this little sheet, and I probably will. So here is a bullet with an upward speed of 900 meters per second. It has a mass of 15 grams. It hits and travels through a block. Here's the mass of the block, and that was initially at rest. So notice they gave me their speeds and their masses, so I know their energies as well as their momentums. The bullet exits the top of the block, still traveling upward, but with a reduced speed. How high would it go? Now, maybe at first you're not really sure if I should do this with energy or momentum. Maybe writing both of them out. I'll start with the energy. If I said 1/2, and I'll put mass of bullet times velocity of bullet squared plus 1/2 mass of wood times the initial velocity, I should have put initial velocity of the wood squared, which, by the way, is 0. Then I would have, I guess, those same two terms on the other side of the equation. Let me give myself a little more space. I'd have a 1/2, and I'd have the mass of the bullet, and then the final speed of the bullet, plus the 1/2, the mass of the wood, times the final speed of the wood. But don't forget, there would be rubbing between the bullet and the block, which is going to create some heat. And you can see then that even though they've given me all the initial stuff, they haven't given me the final speed of the wood after the impact, which is what I'm thinking I really need because it says how high will it go, so I'd like to know that number. But I can't solve for that number because I also don't know how much rubbing is going on. So there's two unknowns here. And so I'm going to run into a dead end if I do the energy. Of course, if I forget there's rubbing going on, I might not realize this is a dead end, and I'll get a very, very high speed because that's like saying none of the energy went to rubbing of this bullet. But a lot did. Look how much the bullet slowed down. It went from, almost a Mach 3, maybe closer to a Mach 2, 2.5, to just over Mach 1. And so this bullet really slowed down. So there's going to be a lot of rubbing and a lot of heat. So to pass this up is a big mistake. So let me think about the momentum instead. And so the momentum would say the mass of the bullet times the velocity of the bullet initially would then interact with the wood. And so the mass of the wood times the velocity of the wood initial. And again, I'll just remind you that's 0. Is then going to equal the mass of the bullet times the velocity of the bullet after the interaction, and then the mass of the wood times the velocity of the wood final. And in fact, hopefully you didn't spend too much time on the energy, because what's neat about this is no matter what kind of interaction you have, in terms of elastic or inelastic, sticking together or not sticking together, so in this case, I guess they don't stick together, but also they produce heat, so it's an inelastic. It's not a perfectly inelastic, and it's also not elastic. It is just a inelastic. There is some heat. So the energy equation doesn't get me anywhere. In fact, I'll use that same thinking on the next one, where we're really doing the same thing, except things are rotating instead of translating. But you can then see that because momentum doesn't have this extra energy, an extra term, there's only one momentum. There's many different types of energies, but there's only one momentum. You can see that then there's only one unknown here. And that's going to be then my golden process and my golden equation. So let me take the mass of the bullet, 0.015. And the initial velocity of the bullet, 900 meters per second. And just for completeness, I'll put a 0 for the initial momentum of the block. But then the mass of the bullet, or the new velocity, so the bullet still is our 15 grams, but it has slowed way down to 375, which still over Mach 1. So I don't know if I'd say it's going slow, but has slowed way down. Now, the block of wood is really heavy, almost 5 kilograms. So that's why the speed of this wood block after the impact is not going to be that great, which is because the mass is so big. And so in other words, it absorbs a lot of momentum with very little speed. So if I take these numbers, 0.015, and multiply it by 900, and then subtract, moving this over, 0.015 times 375. That's those two together. So then if I divide that by the 4.75, we're looking at a speed of about 1.66 meters per second after the bullet passes through. So the bullet keeps going really, really fast. And the block then kind of jumps up. So the block going incredibly slow compared to the bullet. So the bullet keeps going up, going really fast. But the block's got some speed, and it's going to jump up to some height. At which point, when it says how high it can go, let me get some more space for my work here. My yellow pad, and put a line under here. So now this is the 11B. We can figure out how high it goes by either going back to our kinematics, so V squared final is equal to V initial squared plus 2A times however far it moves. And so we know its final speed of the block goes up. We just know its initial speed on the way up. That's what we just solved for. So this might be the best one to do. However, the other one that says, let's take the kinetic energy that the block now has. And so let's not worry about all the energy from the initial part of the bullet. So I'm not looking at the initial velocity of the bullet, which, as we said, some of it went to heat. And I might point out, now that we know it, we could actually put it into here and figure out how much heat we have. And that's actually the next question. Except we're not talking about translating objects, we're talking about rotating objects. So we'll actually do this on the next problem. But thinking of just the energy involved in the block after the impact, all of that kinetic energy is going to become gravitational potential energy as it goes up. And the masses would cancel off, and you can see that you could calculate the final height by taking the speed and square it, so speed of the wood final, and divide it by 2 and divide by g, which, by the way, is what you would have got if you solved this, right? Because the final speed would have been 0, and so you would have had your initial speed on its way up squared, which is the final speed after the impact, and then you would divide it by a 2, so there's the 2, and then you would divide it by the acceleration, and something with a upward movement is being then accelerated downward by the 9.8. So whether you use the kinematics from before this test or whether you use conservation of energy really doesn't matter at this point. I'm not looking for one way or the other. I was looking more for about a momentum here. But like I said, more along the materials of this test, maybe you would do it this way. And so let me take that speed and square it, and then divide by a 2, and divide by a 9.8, and it looks like about 14 centimeters. So 0.14 meters is how high it goes. Okay, let me just get rid of this piece of paper, because I think we'll need a clean one to finish up the test on the last one, which is the free response number 3. And so free response number 3, and I think you can see the interaction. And my little hint to you was when you do the rotational mechanics, try to pause and go back and say, what would I done if it was translational mechanics? That's why I tried to make this third one a lot like the second one. The second one was translational, and the third one now becomes rotational. But what you end up having is two objects interacting, okay? And the same logic that I just went through is you might first look at these two and say, let me do conservation of energy. But without going through the same lecture, we argued, I guess it was before I got to the extra here, we argued that if you think about the energies, you're going to get stuck because there's going to be a final speed and a heat. Now, for this one, since the two come together, this is a perfectly inelastic. And so those are a little bit easier. In other words, you wouldn't have two different final speeds. You would just have one final speed. So that'd make it a little easier. But still, you have a final speed, which is unknown. And you also have the amount of heat when the things kind of rub on each other. And so one's going clockwise or counterclockwise, and the other one's going clockwise. And so when they come together, there's rubbing. And so there's a lot of this. And so again, if we were to write out the equations for energy, we're going to get stuck. Which is why, hopefully, you're thinking about momentum, because momentum doesn't have that issue. In fact, we can then use the momentum to come back and put it into speed to find the heat. And we have an interaction of two objects. And so I keep coming back to this one because this is how we thought about it for translational motion. And I'm encouraging you to try to think about it the same way here for rotation. So what I'm going to do is say the initial angular momentum is equal to the final angular momentum. And so I'll say it again. I'm thinking about momentum, okay? Now, it's angular momentum because we got rotating objects instead of translating. But nonetheless, here's what we have. So I would do something like this. I would say the I of the first disk times the angular speed of the first one initial plus the I of the second plus the angular speed of the second initial must equal to I in the final speed plus I of the final speed. But as I said, we might as well think of it as one object with one final speed. So I'm going to say the I, after they're brought together, is just the two added here. So before I can actually do this calculation, maybe I should come and do a side calculation and say, okay, what is the moment of inertia of the first one? And so we got to go back to that chapter 10. We got to go, okay, what kind of figure, what kind of shape do we have? We have the disk. I believe it's that second one down that says it's 1/2 mr squared. And the other one, fortunately, is also a disk. So I can get both of these. The only thing I'd want to remember is they don't have the same mass and they don't have the same radius. So I better put a 1, a 1, a 2, a 2. And so grabbing my calculator, I will go 1/2. And the mass of the first one, the first disk has a mass of 1.15. And a radius, and again, we're back to our watching our units, 25 centimeters, which I'm going to type in as 0.25 and square it. So I will get a number of 0.0359, and the units would be kilograms, and the distance would be meters squared. And again, a little comment about the unit, especially since Part B says, look at the heat. Heat is measured in joules. Joules has meters in it. So I just got to watch my units. Now, the other one would be 0.5 times its mass second disk has a mass of 0.9 and a radius of 0.2 when I do it in meters. So this would be 0.018. In fact, that's really half as much, because 18 doubled is 36. So we're almost there. All right, so they don't have the same inertia, and rightfully so. You can tell that. The second one is got less mass and less radius. So for both those reasons, it has less inertia. Okay, so now I can actually then do this step. All right, so I will take the 0.0359 for the inertia of the first one, and its speed would be, and I guess I have a decision to make. It says it is spinning clockwise at 25 RPMs. So two things here. The tradition is that clockwise is negative, and I'll stick to that because the other one is spinning counterclockwise. So one has to be positive, one has to be negative. It doesn't matter which one you choose, but probably easier to stick to tradition. So I'm going to put a negative, and then maybe I need to come back and go, oh man, 25 revolutions per minute. A revolution would be 2 pi radians, and a minute would be 60 seconds. So doing a unit conversion, what I call a direct substitution, put in the meaning of a minute. A minute is exactly equal to 60 seconds, so substitute it in. And a revolution is 2 pi radians. And that's going to give me the speed that I want in the appropriate units when I'm doing energy. Now, technically in A, I'm not really doing energy. So you could probably, if you wanted, leave each of these in RPMs, and get an answer in RPMs. But eventually we're going to have to go to radians because we are looking for the energy lost, and we're going to report that in units of a joule. So I'll go ahead and just change it right here. So 25 times 2 times pi, then divided by 60, gives me a 2.62 radians per second. And I'll put that down here, 2.62 radians per second, and negative for the initial speed here. And the other one, number 2, as we said, had a smaller moment of inertia, and its speed was 15 RPMs. So maybe I'll squeeze it in here. 15, and remember a revolution is 2 pi radians, okay? And if it's revolutions per minute, a minute is 60 seconds. So that's how I'm going to get it into radians per second. So 15 times 2 times pi divided by 60. So this is going to be a plus 1.57. And notice the plus because it says it is spinning counterclockwise. All right, so I'll put here plus 1.57 radians per second. And then that's supposed to equal the 2 added together, so 0.0, what was it, 359, and 0.0180, and then final speed. Okay, so maybe I'll do this first line and just hit enter and see what I've gotten for the total angular momentum. So this is 0.0359 times a negative 2.62. And then plus a 0.018 times 1.57. So if I hit enter, I have a negative, not a surprise, angular momentum. In other words, this has more angular momentum than that one, which again makes sense. It's got more inertia and it's going faster in, of course, the negative direction. All right. Then to get the final speed, I just need to divide by the sum of the two, 0.0359 added to 0.018, and that's going to be a negative speed. And that makes sense, negative, because again, I would expect it to have a negative angular momentum or a clockwise direction of rotation. Now, if you had left this in units of RPMs, of course, you would have put a negative 25 here, and you would have put a plus 15 here. And you would have gotten, let's convert it. Let's see, for radians, I would have to then divide by a 2 and a pi. And then to get it to a minute, I would have to have 60 seconds on the top. And so it looks like a negative 11.7 RPMs is an option too. In fact, now that I think about it, since we didn't do energy, we could have even done this inertia, leaving it in centimeters, because as long as we do it both left and right, they'd cancel off. So technically, I guess A doesn't really need to involve any unit conversion. But I might as well have done it because I think I'm going to need it then to do the harder one here, B. I guess it's the harder one. It's 2 steps, but A kind of helps us out. So anyways, this would be the angular speed. So now to finish this problem, looks like I'll need some extra paper here. I might go, okay, what is the kinetic energy initially? And that would be 1/2 I1 times omega 1 initial squared. And so that's one spinning disk. And then we would have the other spinning disk. And fortunately, we've done, I think, most of the hard work because we've converted all of these already to the units that would be appropriate to get joules. So I'm just going to go 1/2 times I1, which was that 0.0359. That was this one. And then speed squared, which we said was this negative 2.62. And we're squaring it, so I won't even bother to type in the negative, but 2.62 squared. So that's the first term. Let me add that to 1/2 times the inertia of the other one, 0.018, times its speed, which we said was 1.57 squared. And so if I hit enter, it looks like we've got 0.145 joules of energy before there's any rubbing going on. And so it's just spinning there, rubbing against a frictionless y-axis. And it would stay that way forever if it was frictionless, until they meet up. Then there's friction and rubbing. And one, I guess they both end up slowing down because they're going in opposite directions. But ultimately, they would spin together in the negative direction. Okay, now, afterwards, thinking of them as one object, I can just add their inertias together and then the final speed squared and get the kinetic energy. So let me add them again, 0.0359 plus 0.018. So that's this term, the moment inertia of the two together. Let me multiply it by the 1/2, and then let me multiply by the final speed, which we said is a negative, and I won't worry about the negative. Since I'm going to square it, it'll go away. 1.22. So 1.22 squared. And it looks like afterwards I've got something quite a bit less. And of course, that's the reason why is because whatever energy you started with, the initial kinetic energy, must show up on the other side, which would be final kinetic energy and this rubbing or this heat energy we're looking for. And so this is just like the one we did in the lab with the ballistic pendulum, and that we shot that ball into it. We used this idea to find the heat. And so hopefully that lab we did kind of helped you through this hard problem. I think the hardest one on the test, because it has the two parts. It's got the unit conversion, and rotations in general are just harder. All right, so taking this number up here and subtracting this number, I'm looking at about a 10.5.105 joules. It would be the answer for B. All right, well, I hope you learned a lot going through this. If there's anything you missed, hopefully you learned it and you're better off for it. I guess if you didn't miss anything, great. But even if you did, at least now you know it and you won't miss it on the final exam where the test is worth more than these individual ones. Okay. I'll call it quits. Bye now.